Yeah, Assalamualaikum and good afternoon to everybody. So today I'm going to continue on our lecture from yesterday, which is the first part of thermodynamics, which is thermodynamics 1, when we're going to discuss about temperature, heat, and Zeroth Law of Thermodynamics. So without further ado, I would like to go through to the part where we left off yesterday. All right, but before that, I'll just go through the things that we have covered yesterday, all this course evaluation, introduction, and all the topics that we will cover. So yesterday we have looked at the definition of thermodynamics. So in this slide, we look at the definition of thermodynamics and then look at some of the example and history regarding the study and research in thermodynamics. I have highlighted and make it obvious to you all that thermodynamics is very important, although you have some of you, in fact most of you, have not learned about it before. But we need to appreciate how important thermodynamics is for science and technology as well, because all of the physics, modern physics, and also all of the industry, the development and progress in industry in the world is due to the study in thermodynamics. Okay, because of thermodynamics, we have discovered the concept of atoms and how atoms behave, and from that, we also get the theory of relativity and nuclear physics. Okay, and on top of that all, which is more relevant to us, is that all the applications around us is due to thermodynamics. Like for example, all the electrical equipment in your house, like your refrigerator, your air conditioner, the cars that you are using, the motorcycle that you are using, the aeroplane, the rocket, everything that has got to do with the conversion of energy from one domain to another domain, everything is got something to do with thermodynamics. Okay, so thermodynamics governs the conservation of energy. Okay, what you have studied before in Newton law, those are the conservation of mechanical energy. But in thermodynamics, we cover all the different types of energy and also domain of energy, in particular thermal energy, and also how thermal energy is converted into other domains or other types of energy. And one example, which is the most important now, is converting thermal energy into electrical energy or mechanical energy. All right, and then in this introduction, the most important things that I need you to understand and absorb by the end of this lecture is the definition of some concepts relating to thermodynamics that you will encounter time and again as we go along until the end of this section. Okay, so the first one here, the first two are basically the definition of thermal energy and also heat. Okay, and it's important that you know that thermal energy is not the same as heat. All this while we might be using the word heat wrong. So although in terms of language it's not wrong, but in terms of the definition in physics, heat does not mean hot, or heat does not mean thermal energy. Thermal energy is the type of energy similar to, you can have mechanical energy, nuclear energy, radiation or electromagnetic energy, magnetic energy. You can have thermal energy. Okay, and then this thermal energy can be propagated or can be transferred within an object or from one object to another object through the transfer of heat. So heat here is very important that you know that heat is the energy transferred between substances. Okay, it's the energy transferred, and what kind of energy that is being transferred is thermal energy. And then the requirement for heat transfer is that there must be a temperature difference. Okay, so the first requirement, there must be a temperature difference, and then the second requirement is that heat transfer always flow from hot to cold, or in another words, it is always moving from a region or object with a higher temperature to a region or object with a lower temperature. All right. So heat as a form of energy transfer, types of energy in material. We know that energy, the type of energy can be kinetic, potential, electrical, and so forth. Those are related to macroscopic, structural. Thermal energy in particular is concerning microscopic energy. So when you say microscopic energy, you are actually looking at how the individual atoms of molecules that make up an object or matter, how does it behave, how does it move, how does it rotate or vibrate. Okay, and then this movement of the atoms and molecule collectively in your matter or in your object will give rise to thermal energy. Okay, so the molecular movement of atoms and molecules can be molecule translation, molecule rotation, vibration, and also intermolecular energy or force. Okay, so if you want to know in detail about each individual type of microscopic energy, you can look into the book. Okay, so I will not cover it here. So when you say heat is being transferred, the transferred heat energy is the sum of all of this microscopic static energy. Okay, so when you take into account the kinetic energy of the molecules and atoms, the way it rotates, the way it vibrates, everything is combined into a single thermal energy. And it can be transferred between systems. So thermal energy can be transferred between two systems, okay, as heat. So heat is being transferred, or it can be transformed into mechanical energy, whereby it is extracted as mechanical work. So we look at the first definition of one concept. So a concept that you need to know, the first one is thermodynamic system. So what is a thermodynamic system? Thermodynamic system is a quantity of matter or region in a space chosen for study, okay, whereby this system must consist of the substance. So the substance must be any kind of matter regardless of the phase. So it can be a solid, it can be liquid, it can be gas, or it can be plasma. So it must have a substance. It must have so substance is also matter. It must have a physical matter. It must have a boundary, and it must have a surrounding. So you need to, in any system, you need to identify these three things. What are the substance? What is the boundary? And what is the surrounding? Okay. And thermodynamic systems, for our study in this course, we will identify and classify thermodynamic systems as three types, which is open system, closed system, and isolated system. Open system is whereby both the matter and energy can go in and out from the substance to the surrounding, or the other way around, so vice versa. So energy and matter can interchange between the substance and the surrounding through the boundary. Okay, that is for open system. In a closed system, only the energy can be transferred to and from the substance and surrounding through the boundary. And then in an isolated system, the last type of system that we will look into is a system whereby no energy or substance can interchange between the substance and surrounding. Therefore, the boundary is acting like a virtual insulator. It insulates the energy and the matter inside the substance. Okay, the surrounding will have no thermodynamic process with the substance itself. Okay, so in a thermodynamic system, how do we classify or describe a thermodynamic system is through by knowing what are its physical properties. So in a thermodynamic system, the physical properties that you need to know are all these, okay, mass, volume, pressure, density, and temperature. And there are other types of properties as well, which are internal energy, enthalpy, entropy. Okay, so we will go through all of these parameters as we go along. So by knowing all the condition or the parameters that describes this thermodynamic system, we can define the state of a system. So a state of a system is basically when you know what are the measure, or what is the measurements of all the properties that that we have highlighted just now. Okay, what is the mass, what is the volume, temperature, and etc. So by knowing what are the measurements, we can identify and classify the state of the system, or we can describe the state of the system. Now, the state of the system is in equilibrium if the values of all the properties that I mentioned just now are the same all over the system and do not change. So if we go back to the previous slide, if all of these properties at any particular time is constant, is stable, then we can say that, okay, that thermodynamic system is in equilibrium. Okay, and a state can exist out of equilibrium if any one of the properties changes. But we can do some sort of approximation to make sure that we can describe the changes and describe the state of the system, or how the system is behaving even though it is changing. Okay, you need to appreciate that inside any thermodynamic system is very, very difficult to measure each one of these properties precisely. Okay, so therefore we need to do some sort of approximation. As we go along, we will see what kind of approximation there are. Now, so let's look at another concept, which is thermal equilibrium. So this is another very important concept that you must grasp. Okay, so thermal equilibrium is basically a state of a system, or state of a thermodynamic system, whereby everything is in equilibrium. But how do we define it? Okay, we define thermal equilibrium is when the first way to describe it is a situation which two objects will not exchange energy by heat or by electromagnetic radiation if they were placed in thermal contact, or the net exchange of energy by heat transfer within a system or between system is zero. So that is meaning to say that if two objects are at the same temperature, then they are in thermal equilibrium. Okay, so it is concerning the temperature. So you need to look at the temperature to know whether an object or a system or two systems are in thermal equilibrium. Okay, the next concept that we need to look into now also is an insulator. So in thermodynamics, when we describe an insulator, we are saying something which is acting like an ideal insulator. So an ideal insulator does not exist, but we can approximate it, or we can assume that an ideal insulator is something that will prevent thermal equilibrium to occur, or it will prevent heat transfer between two objects or within two region of an object. Okay, so an insulator minimize heat transfer, and we use insulator to avoid thermal equilibrium. We don't want heat exchange between two bodies. Okay, so an ideal insulator will have zero heat transfer, which does not exist in the real world. But there is something very, very close to an ideal insulator. Now, by understanding thermal equilibrium, we can describe the zeroth law of thermodynamics. Why does we have a zeroth law of thermodynamics? Well, historically, okay, people come up with the concept of the first law of thermodynamics, and then the second law of thermodynamics, and then they also have the third and the fourth law. But historically, the most important ones are the first and the second. And then when physicists find out some sort of a discovery that require a further definition of behavior in a thermodynamic analysis, they come up with new laws. So that's how you can get third law and also the fourth law. Okay, but the main one is the first and the second. So how does the zeroth law of thermodynamics come about? It comes about after the discovery of the second law. So people actually know this phenomena, but they have not actually come up with a proper definition or law to describe this phenomena. But once they have done a lot of analysis and research, they realize that we need to define this. We need to define this phenomena. We need to create some sort of convention or law to describe it. And hence, that's how you get the zeroth law of thermodynamics. So what is a zeroth law of thermodynamics? Off the bat, I can mention to you it is regarding thermal equilibrium. So that's the word that, or the concept that should come up in your mind when you hear or read zeroth law of thermodynamics. It's about thermal equilibrium. And we know that thermal equilibrium is concerning concerning temperature. Okay, so let's look at this experiment here. Okay, so let's we have op so we have figure 1 and figure 2. So in figure 1, okay, let's say we have object A, B, and C. Okay, A and B is separated. Okay, so A and B is separated by an insulator. Okay, this is the insulator. And then both A and B are connected to C by having a conducting plate in between them. Here, so this is a conducting plate. So that means heat exchange can happen between A and C and also can happen between B and C, but no heat transfer can directly occur between A and B. So if object A and B are separately in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. So what does this mean? It means that even though A and B are not in contact or not in physical contact, or no heat transfer can occur between A and B, but if we know that A and C are in a thermal equilibrium and B and C are in a thermal equilibrium, that means both A and B are in thermal equilibrium with the same third object, which is C. That means we can conclude A and B must be in thermal equilibrium as well. Why? Because they are both in thermal equilibrium with the same third object. So it's the description you might find this description to be like a no-brainer. That means everybody know this, right? If A and C are at the same temperature, B and C temperature, same temperature, that means A and B must also be in the same temperature as well. Yes, you are right. By observation, you know that. By experience, you know that. But that is something that we need to define. So the zeroth law of thermodynamics states that two systems are in thermal equilibrium if and only if they have the same temperature. So ultimately, this is a statement to describe the zeroth law of thermodynamics, which is a law to determine whether an object is in thermal equilibrium or not. And to know if it's in thermal equilibrium or not, we look at the property temperature. And if the temperature is the same, that means the two objects are in thermal equilibrium. So it's a very easy and straightforward law. So that is the zeroth law of thermodynamics, which is two systems are in thermal equilibrium if and only if they have the same temperature. Okay, so this one is the same kind of experiment. Okay, but in this particular experiment, it's more practical, whereby you have object A and B, and then you have the third object C, and the third object C here is your thermometer. So imagine you have a digital thermometer, you measure A. So when you measure A, what will happen? Actually, some of the heat is transferred into the probe of the thermometer until the probe of the thermometer will have the same temperature with A. Then only it gives out the final reading. All right, and if you do the same thing to an object B, and if you look at the reading to be the same, that means A and B is in thermal equilibrium. Okay, so speaking of thermometers, we also need to identify what is the tool, the equipment that we use to measure temperature. So a thermometer, you know, that is something that is used to measure temperature of a system, right? So what you need to know is the principle of thermometers, because the way you measure temperature can have different type of method, sensing method. Okay, and then most of the sensing method in a thermometer is based on the principle that some physical properties of a system changes as the system's temperature change. What are the properties of a system that can change if you change the temperature? Those properties are, for example, volume. When you increase temperature, the volume will increase because the expansion of matter. Or if you reduce the temperature, the volume will decrease because the matter will shrink. All right, so the volume will change, which basically the change in dimension. And also the pressure of gas at a constant volume can change. Volume of a gas at a constant pressure can change. The electric resistance of a conductor can change, and this is what we call thermoresistive effect. So if you want to know the actual the actual thermoresistive effect. Okay. And then color of an object. Color of an object can change. All right. If you heat up metal up until certain temperature, it will glow a red color. So that is just one example. But other kind of object can change its color very easily, even if you change the temperature by a few degrees. Okay, so by knowing how these properties change with temperature, we can correlate between the change in physical properties into what is the corresponding temperature. So a temperature scale can be established on the basis of any of these physical properties. So this is the most common thermometer that I think all of you have come across, which is liquid in glass. Okay, inside the tube, all right, there is no gas. Okay, it's in vacuum. All right, so there's no gas. The column where you have mercury, so in this case we fill the thermometer with mercury, and inside the column where the mercury reside, there's no gas, so it's in vacuum. So there is no force opposing the expansion or the shrinking of mercury. Okay, sometimes we use alcohol as well. A thermometer can be calibrated by placing it in contact with some natural system that remain at constant temperature. So we know that expansion of solid or expansion of liquid and the contraction of it uh, is the direct result of changing temperature. But how can we know what temperature correlate to what kind of shrinking, or what is the scaling of the expansion? That is when we have to calibrate the temperature. We have to calibrate to know what temperature it actually is. Okay, so normally thermometer is calibrated by placing it in contact with some natural system that remains at constant temperature. Common system involve water. For example, we can look at the ice point of water. We know ice point of water is 0 degrees, and then steam point of water, we know it's around 100 degrees. So once we know these points and we know where it is, so here is 0, and then up somewhere here is 100, then we can work out the scale and then divide the difference between 0 and 100 by 100 scales. So then we can have our thermometer. So that's how we do it. Okay, so ice point 0, steam point 100. The length of the column between these 2 points is divided into 100 increments called degrees. Now, the problem with liquid in gas thermometer that you have seen just now is that an alcohol thermometer and mercury thermometer may agree only at the calibration points, which is between these two temperatures, right? The discrepancies between thermometers are especially large when the temperature being measured are far from the calibration point. For example, if it's too hot or too cold, sometimes the expansion or the contraction of the liquid will not be linear anymore. Okay, so when it's not linear, that means the scale is not linear. So that means the measurement that you make or whatever that you read from the division of the scale is not correct. The thermometers have also have a limited range of values that can be measured. Okay, for example, mercury cannot be used under minus 39 degrees Celsius. Alcohol cannot be used above 85, because above that it will start to evaporize. Now so you have looked at liquid thermometer, which is you are familiar with. There is another type of thermometer that we use in the lab to determine the actual temperature of certain liquid, for example, which is called a constant volume gas thermometer. All right, so let me just change this a little bit so you can see. Okay, so in this apparatus, as you can see, this apparatus here is your constant gas thermometer. The physical change exploited in the variation of pressure of a fixed volume gas as its temperature change. So in this thermometer, we look at how the gas is applying pressure on a fixed volume of gas. So if we can maintain the volume of the gas fixed, that means any change of temperature will change the pressure of the gas. So where is the gas? The gas is inside here. So you have the gas inside here, right? Inside this column. So this is all the gas. Now this gas is trapped inside this column, and then you can have a liquid. So in this particular liquid you have mercury. So you have mercury blocking this gas. Okay, so it does not escape. And then what will happen is that if you cool down, or if you change the temperature of the liquid at which you immerse the gas inside, all right, the pressure will change. So first of all, the volume might change. All right, so the volume will change. So what you will do is you will have to move this part of the thermometer up or down in order to make the level of mercury on this column to be at 0, so that you can maintain the volume of the gas to be constant. So once you can have the volume to be constant, you measure what is the height of the change in this part of the column, because this height of the change will basically you can find the pressure mgh, okay, of of the of the gas inside the column. All right, so you can read through. So the thermometer is calibrated by using ice water bath and a steam bath water, so you can do the both. All right, so the pressures of the mercury under each situation are recorded. The information is plotted. To find the temperature of a substance, the gas flask is placed in thermal contact with the substance. Pressure is found on the graph. The temperature is read from the graph. Okay, so what we do is that we change the liquid to be in ice or to be boiling. And then we know when it's boiling, it's 100. When it's inside ice, it's 0. So we plot it 0 and 100. And then we can have a straight line. So this should be our line to describe how does the pressure change with temperature inside the thermometer. So the thermometer readings are virtually independent of the gas used. What does it mean? If the lines of various gases are extended, the pressure is always 0 when the temperature is at minus 273.15. So in this experiment, okay, in this gas thermometer, you can change the type of gas you put inside the column. Okay, and the rate at which the pressure change with temperature for different type of gas is different. For example, helium will expand even or will apply a different kind of pressure when you put the temperature of 0 degrees Celsius compared to oxygen, for example. And oxygen is different with carbon dioxide and so on. So every gas will produce a different kind of P versus T graph. So in this particular example, let's say we have 3 trials, all 3 using 3 different gases. So we have gas 1, 2, and 3. So if you plot the pressure at temperature 0 and temperature 100 for each one of the gases, okay, you will get 3 different graph, right? 3 different lines. Now the interesting thing is that if you extrapolate this line, if you extrapolate it until it crosses the x-axis or intersect with the x-axis, what will happen is that you will find out, regardless of the gas, it will intersect the x-axis at the exact same point, which is at minus 273.15 degrees Celsius. All right, so this one is degrees Celsius. Okay, this temperature is called absolute zero. So this is the temperature, a theoretical temperature at which this is the lowest temperature anything in this whole universe can have. Okay, so right now we have never actually seen absolute zero outside of the lab. Okay, so it doesn't exist even in space. All right, but absolute zero is just an idea, or it's just a value that we use to describe a temperature which is zero, similar to how we describe the speed of light, or similar to how we describe infinity. Okay, it's just a value that we use to describe something. It's an ideal value, absolute zero, which is 0 Kelvin. Okay, absolute zero is used as the basis of the absolute temperature scale, which is Kelvin. So Kelvin is the SI unit, is the standard unit when you want to do thermodynamic analysis most of the time. Okay, the only good thing about Kelvin is that it has the same scale measurement with Celsius. To convert between Celsius and Kelvin, therefore you need to use this equation only. So in answering exam questions, if you convert Celsius to Kelvin or vice versa, it's okay for you to use 273 as an approximation. Okay, so even if you don't remember the 0.15, it's still okay. All right, but if you, it's better that you include 0.15. All right. So now let's look at the absolute temperature scale. So we have Kelvin. So some information about Kelvin. Okay, so this is, so here I will not go in much detail, but I will go straight to Fahrenheit scale. So you have looked at, you're familiar with Kelvin, you're familiar with Celsius, and then there's another scale which is Fahrenheit scale. This is a common scale in everyday use in the USA, in America. Okay, where they record the temperature of ice point is 32 degrees Fahrenheit and temperature of steam point is 212 Fahrenheit. There are 180 divisions or degrees between the two reference points. Comparison of Celsius and Kelvin have the same size degree but different starting point. Celsius and Fahrenheit have different size degrees and different starting point. So to convert between Fahrenheit to Celsius, you have to use this equation here. And then to compare changes in temperature, you use this, okay, this equation. Okay, so in describing everyday life, Fahrenheit is an acceptable scale to use, although I think it's not scientific at all, due to the reason that the scale changes as you go along the boiling point and also the cooling point of water. This is because Fahrenheit did not use water, but it used different type of liquid in doing the calibration. All right, so that's why in science, when you do scientific calculation, you never use Fahrenheit. You always use Kelvin, and sometimes you can use Celsius as well, because at least it is the same scale. Now here for the next section, we look at thermal expansion. So here I will not go in detail. I will just go through it very fast because I think you have covered this in your material science. The thing that you need to understand is that every object, especially solid, will expand if you increase the temperature and it will contract if you reduce the temperature. So thermal expansion can be measured if we know uh, the coefficient of expansion. Okay, so the equation is like this. All right, so you can have linear expansion. Linear expansion is applicable when you have an object that has a fairly huge or fairly large aspect ratio. What does that mean? It means that the width and length will have a very high ratio. For example, if the length is 100 and the width centimeter, and then the width is 1 centimeter, you can consider this to be an high aspect ratio object. So for an high aspect ratio object, or a piece of wire, okay, a piece of wire is a high aspect ratio object. So if you apply any change in temperature, the expansion of the length is more than the expansion of the width. So therefore the expansion of the width can be neglected. So you approximate the expansion with linear expansion, whereby we just look at the length, okay, and then we look at the change of the length. So we can know the change of the length by knowing the coefficient of expansion, which is different for different element or different material, and then the initial length, and also what is the temperature change. So that one is very straightforward, and I think you all know that different material have different different material will have different coefficient of expansion. And then you can also have volume and area expansion. So if you are looking at the volume or area expansion, then you have to change the expansion coefficient. So beta and alpha is basically just so alpha is the coefficient of expansion. For you to measure the change in area, you need to times 2 times alpha. And then if you are doing the volume expansion, then it's 3 times alpha. So beta is basically just 3 times alpha. Okay, so here we look at the water's unusual behavior. So I will not look into in detail here because I think I would like you to go to YouTube and just find some videos explaining the unusual behavior of water. One thing that you need to look at is basically how does the density of water change with temperature. So density versus temperature. So you expect as you increase the temperature, a density of gas or liquid should decrease. It becomes less dense. Why? Because it is expanding. So if it's expanding, it has higher volume. The mass does not change. Density is just basically volume over mass. So you expect the density to reduce as the temperature is increasing because the object is expanding. However, for water, the graph is not going down as how it should. Rather, it will go up first, up to a peak, and then only it will follow the standard decrease of density with temperature. So water has a peak density at temperature roughly around 4 degrees Celsius. So the density of water is at its highest when it is 4 degrees Celsius. That and then ice, for example, ice which is less than 0 degrees or at 0 degrees will have a lower density. So that's why when you drink water, ice is always floating in your cup or in your glass, right? So I want you to read to find a YouTube video to describe this even more and see what is the implication and how special water is by having this behavior. So water is only one of a very few, I think the only natural occurring liquid in the world that have this phenomena. Okay, whereby it has an increase in density with regards to temperature between 0 to 4 degrees Celsius. Okay, lastly, we look at a concept of ideal gas and ideal gas. Okay, for gases, the interatomic forces within the gas are very weak. We can imagine these forces to be non-existent. That means in a gas, if you have a balloon, you blow up the balloon, you inflate it, the gas inside the balloon will have a very weak force trying to attract them each other. So the force is very weak, so they are free to move around. So that's how they can have kinetic energy. Okay, note that there is no equilibrium separation for the atoms. There's no standard volume and at a given temperature. So the volume of a gas depends not on temperature but depends on the container that contains it, or depends on the boundary. If the boundary is rigid and the shape of the boundary is a rectangle, then the volume is that rectangle. If it's inside the balloon, then it's the size of the balloon, and so on. For a gas, the volume depends on the size of the container. Equations involving gases will contain the volume as a variable. This is instead of focusing on delta V. Delta V is the change in volume. So we when we are looking at equation involving gas, we just need to know what is the volume, which is the volume of the container. So gas, equation of state. So let's look at the equation of state. It is useful to know how the volume, pressure, and temperature of the gas of mass m are related. The equation that interrelates these quantities is called the equation of state. These are generally quite complicated. If the gas is maintained at low pressure, the equation of state becomes much easier. The equation of state can be determined from experimental results. This type of low density gas is commonly referred to as ideal gas. Alright, so if we want to get an equation to describe the state of a gas, alright, all the properties of the gas, it's very difficult because gas cannot be cannot be measured accurately because you need to individually identify the energy of individual molecule, which is impossible. But we can approximate it and then model it as an ideal gas. All right. So, and then this approximation is only applicable if we are doing it at low temperature. So if the thermodynamic process is occurring very near the room temperature or plus minus 100 degrees, it should be okay as long as the pressure is considerably low. The ideal gas model can be used to make predictions about the behavior of gases. If the gases are at low pressures, this model adequately describes the behavior of the real gas. And then we can quantify the gas by knowing the number of moles. You know that 1 mole is equals to the Avogadro's number, which is basically 6 times 10 to the power of 23 molecules or atoms in 1 mole. All right, and then you can use this equation to know the number of moles relating to the mass, relating to the molecular mass. Right. So we will look at ideal gas model not in this section but in the next lecture. Okay. Now let's look at gas laws. So the basic gas laws that we need to be acquainted with is, first of all, is Boyle's law. Okay, this is a law that relates between pressure, temperature, and also volume. So in Boyle's law, when a gas is kept at a constant temperature, its pressure is inversely proportional to its volume. So if T is constant, then P is inversely proportional to volume. In Charles and Gay-Lussac law, when a gas is kept at a constant pressure, its volume is directly proportional to its temperature. So if P now is constant, therefore volume is proportional to T. Okay, and then the last one, Guy-Lussac's law. When the volume of the gas is kept constant, the pressure is directly proportional to its temperature. Okay. So it might be difficult to remember the names, but another way to describe these laws are, firstly, constant temperature gas law, constant pressure law, and constant volume law. Right? The ideal gas law is often expressed in terms of the total number of molecules, which is n, present in the sample. Okay, so we can have P times V is equals to nRT, which is equals to n over Na. N is the number of molecules. Okay, and then so small n is the number of moles, big N is the actual number of molecules, n subscript A is the Avogadro's number, times R times T. So R is your gas constant. Okay, so we have this equation. So this equation 2.6 is the single most important equation to describe ideal gas law. So this equation describes ideal gas law. So in an ideal gas law, pressure times volume is equals to number of moles times Ru. Ru is the universal gas constant times T. It is common to call P, V, and T the thermodynamic variable of an ideal gas. If the equation of state is known, one of the variables can always be expressed as some function of the other two. R is a proportionality constant or gas constant. Okay, and for all gases, so R is different for gas. Okay, so different types of gas will have different gas constant, but we can have Ru, which is the universal gas constant, which is applicable to all gases. So in the unit of joule per mole Kelvin, this is the value 8.3145. It doesn't change for any gas, or it can be 0.08206 liter atmospheric over mole Kelvin. So we can rewrite 2.6 as this equation as well. Okay, so that is the equation. So we're going to use it a lot after this. So today, in this lecture or in this chapter, we have looked at the introduction of thermodynamics. The important things that you need to obtain from this introduction to thermodynamics are the definition of different concepts, all right? What are the concepts? The concept of thermal energy, concept of heat, concept of temperature, concept of thermodynamic systems, concept of state of the system, the concept of thermal equilibrium, and so on. Okay. And then we look at the zeroth law of thermodynamics. So again, let's recall zeroth law of thermodynamics is the law to describe the condition for thermal equilibrium. And thermal equilibrium is determined by the temperature of the objects. All right. Relating to temperature, and then temperature scale, thermal expansion of solid. So this one I did not cover in detail because you have gone through it before this, and then introduction to ideal gas. So we're going to look into this in more detail afterwards. Okay. So that's all for this section. Thank you very much, and please continue with the next lecture. Have a good day.